chapter 12 for the AP review on physical properties of solutions. Begin with, they talk about supersaturated, unsaturated, and saturated solutions. You may recall this solubility curve that we talked about a lot in Chem 1 and a little bit in Chem 2, that once again, if you're directly on the curve, which measures how many grams of solute dissolved at a certain temperature, if you're directly on the curve, then you're going to be saturated. If you have less than the curve, you're going to be unsaturated. If you have more than what the curve says, like in the NaNO3 example, you could be supersaturated. Recall though, to make a supersaturated solution, usually if we're looking at NaNO3, I have to heat up a whole bunch of solute to have it below the curve, and then I cool it down so it goes above the curve. So simply by adding more than you should be able to, which again, supersaturated is dissolving more than you should be able to, you can't say that it's naturally supersaturated. Because sometimes you're just going to have solids sitting on the bottom because it's dissolved as much as it can, and that's going to be saturated. By the way, crystallization is what you will see in a supersaturated solution if you add more solute. So if you add more solute to a supersaturated, it will crystallize out. Some terms that they bring up in this chapter is solute and solvent. Once again, the solute is the thing being dissolved. The solvent is doing the dissolving because there's more of it. Miscible refers to being able to mix. Immiscible is unable to mix. Solvation is something we didn't talk about a lot, but that's when molecules or ions are surrounded by the water or the solvent. So when you dissolve a solute in a solvent, the solvent usually surrounds the ion. And then likes dissolves likes is a rule that we talk about in Chem 1 quite a bit, that things with charges, polar and ionic compounds, will dissolve other things with charges. Nonpolar, which does not have any charge, can only mix with other nonpolar molecules. There are several different concentration units that we talked about in this chapter as well. The first one was percent by mass. This would be the mass of the solute divided by the mass of the solution. The second one is referred to as mole fraction. This would be the moles of the solute divided by the total moles of the solution. Molarity, which is our most common one, which is the moles of solute divided by liters of solution. And finally, molality is going to be the moles of solute divided by kilograms of solvent. I'll repeat those three again if you need to jot those down. The percent by mass is the mass of solute divided by the mass of the solution. Multiply by 100 to express it as percent. The mole fraction is moles of solute divided by total moles. Molarity is the moles of solute divided by liters of solution. And finally, molality is the moles of solute divided by kilogram of solvent. What I'm going to do is give you a practice problem right now where we have to convert between two different units. Now this is the type of question that we worked on a lot last fall. A tricky question though. You'll notice that I'm giving you a molarity right away and I'm asking for molality. So this is going to require a lot of calculation on our part. The first thing that I notice is when it says 2.45 molar, to me that means I have 2.45 moles of solute for every 1 liter of solution. So I find it helpful to jot down the parts that I need. Now in molality, the thing I want to get to at the end, it's moles of solute over kilograms of solvent. I already have the moles of solute part down, so that's the good news. You'll notice that in this equation it gives you the density of the solution. We need to use that density equation. Density equals mass divided by volume. I'm going to solve for mass. Mass equals density times volume. So if I multiply the 0.976 grams per milliliter, and I multiply it by 1,000 milliliters, that will give me 976 grams. That is of the solution though. So I can't just right away plug that into molality because molality is kilograms of solvent. The way I have to figure out that part is if this is my grams of solution, I can convert my 2.45 moles of solute into grams of solute and subtract it from there. So now 2.45 moles, I'm going to convert that into grams. I look at my periodic table and the mass for methanol, which is CH4O by the way, the mass of that is going to be 32.05. So now 2.45 times that number is going to get me 78.5 grams of methanol, CH4O. My total solution is 976. The solute is 78.5. I'm going to subtract the two. And when I subtract the two, if I round off, I'm going to get 898 grams. So now, again, I'll rewrite it up here, 898 grams of just the solvent. Now that I know my grams of solvent, I know my moles of solute, now I can divide the two. So the last step in this problem is go back to the 2.45 moles of solute divided by the 0.898 kilograms. Again, hopefully you don't need a reminder on how to go grams to kilograms. And that'll give me a final molality of 2.73. Lowercase m for molality, what's the formula? CH4O. Again, the key to this sort of problem is knowing what does molarity mean. It means 2.45 moles in 1 liter of solution. When I had to get to molality, which was moles per kilogram of solvent, I really had to convert this into kilograms of solvent. Use density to get grams of solution, subtract the grams of the solute, then you're there. The next thing we're going to go over is temperature's effect on solubility. The first thing we talked about is something referred to as fractional crystallization. Fractional crystallization is dealing with the fact that when you have something and you cool it down, it will start to crystallize out. So if a solution was at one point unsaturated and then you cool it down, it can become saturated. So again, if we use the NaNO3 example, if it's below the curve, it's unsaturated. As you cool it, it becomes saturated. And then when it's above the curve, if it doesn't supersaturate, it's just going to crystallize out right away. Now, if you had a mixture of different solids, what you could do is by knowing the solubility of different solids, cool them down and one of them would dissolve, or undissolve rather, first than the other one. Gas solubility in this curve is a little unusual. You'll notice for NH3, it is the only line in this curve, well, one of the only lines in this curve, that decreases. It goes down as temperature increases. Most things, as temperature increases, so does the amount that you can dissolve. The reason being is molecules move faster at higher temperatures, and if molecules move faster at higher temperatures, they're able to grab hold of more solutes. Gases, though, are the exact opposite. Gases are difficult to hold on to in the first place. So really, you need the gas molecules to be moving slowly. Lower temperatures mean gas molecules are moving slower, and that's how you can actually dissolve more gas at a lower temperature than at a higher temperature. Last thing to mention on this slide is Henry's law. Again, I'm uncertain if you're going to have to solve for Henry's law, but it's referring to the pressure's effect on solubility. So this graph is just talking about temperature's effect on solubility. This equation is referring to, instead, pressure's effect, where the C stands for the concentration, typically molarity. K is the Henry's law constant, and P is the pressure in atmospheres. One of the things we talked about quite a bit in this chapter is colligative properties. Colligative properties are properties that depend on the number of solute particles in solution and not the nature of the solute. First one we refer to as vapor pressure lowering, which we talked about Raoult's law, which the X1 is the mole fraction. So the big capital X is usually referring to mole fraction. P1 is going to be the new pressure, and P1 naught is going to be the original pressure. So when we talk about something lowering its pressure, here's a sample problem. It says calculate the vapor pressure of a solution made by dissolving 82.4 grams of urea, and there's the molar mass, in 212 milliliters of water at 35 degrees Celsius. The pressure originally is 42.18 millimeters of mercury. What is the vapor pressure lowering? So what we can do is we can figure out the mole fraction. We can then multiply it by that original pressure and figure out what would be the new pressure of that solution. The vapor pressure lowering part would be subtracting then the original from the new. So we're going to go over to the board and do that. We're going to start off by converting our grams of urea into moles of urea. 82.4 grams of urea. Convert to moles by doing 1 mole over the 60.06 grams. And that will give me a number of moles, a 1.37 moles. Mole fraction, though, requires that we not only know the moles of solute, but the moles of solvent as well. If you recall, water's density is 1. So the problem says 212 milliliters of water. I can call it 212 grams of water just the same. The conversion here is 1 mole over 18.02 grams. That will give me a moles of water, 11.76 moles. I'm going to add up my two number of moles to get my total number of moles. Mole fraction is the part divided by the total, so I need the total number, which in this case is 13.13 moles. Now, as I stated before, mole fraction, which is represented by X, is typically moles of solute over moles of solution. This is a little different in this case though, because I want to see how does water change. So I'm going to have moles of water over moles total. So here's my moles of H2O over 13.13 moles total. That I'm going to then multiply by the 42.18 millimeters of mercury. And when I solve for that, I'm going to continue up on top here. That's going to get my P1 to equal, because remember this is X1, this is P1 naught. That's going to get my P1 to equal 37.27 millimeters of mercury. One thing to check and make sure of, vapor pressure lowering means when you add a solute to water in this case, the vapor pressure should go down. So it started at 42.18, it's now at 37.27. So the new pressure, here's your answer. If I wanted to solve for the vapor pressure lowering, I would take 42.18, my original pressure, and subtract 37.27. That would get how much did it lower by, which in this case is 4.91 millimeters of mercury is the vapor pressure lowering. So these are your two answers that you had to solve for in this one. What is the new pressure? What is the vapor pressure lowering? Once again, the mole fraction usually is moles of solute over total moles, but when we're talking about how is water changing, we want moles of water over total number of moles. The next slide is giving you a picture of what fractional distillation is. Fractional distillation is defined as separating liquids based on their boiling point. So what you'd have in this round bottom flask is a couple of different liquids, and you heat it up. Typically a thermometer tells you the temperature of the steam. So once again, just like some substances are more or less soluble at different temperatures, some substances are going to evaporate at different temperatures. So if I have a mixture of liquids, one of them is going to start to evaporate. I would measure that with my thermometer, and then you see this tube here. What happens is it gets into the condensation chamber, which in college chemistry you'll have a water line going in and out to cool down that gas. It cools down that gas to turn into a liquid, and you collect that liquid. If you keep the temperature at a constant temperature when it starts to boil, you will get all of one liquid gone, and then you can get the second liquid later. But that's what a fractional distillation would look like. The second colligative property is referred to as boiling point elevation. I'm not going to actually show you a calculation for this one. Delta TB, again, is referring to the change in boiling point, which boiling point will go up when you add a solute. The I is referred to the Van't Hoff factor. We talked about the Van't Hoff factor before, but basically, when we're talking about these colligative properties, why freezing point can go down, boiling point can go up. This is because of something referred to as disorder. We talk about thermodynamics disorder later on, and what this mentions is that when you have pure liquid, when you add a solute to it, it changes the properties of it. Now think about NaCl, Na plus Cl minus. There's two particles within NaCl. That would be the Van't Hoff factor there. So there's two particles that can affect water's change. Calcium chloride is CaCl2. One calcium, two chlorines. There's three particles, which would be the Van't Hoff factor there. Kb is a boiling point constant for water, which is 0.52 degrees Celsius per molality. Lowercase m is molality. So again, all we do is multiply the Van't Hoff factor times the Kb times the molality of the solution, and that would tell us how much is the boiling point raising by. Freezing point depression, you'll notice a very similar equation. Delta Tf equals I Kfm. Once again, I is the Van't Hoff factor, so how much is affected by how many particles there are. Molality is also a measure of concentration of particles. Kf is the freezing point constant, which for water is 1.86 degrees Celsius per molality. And this will tell you how much the temperature will drop by. Everyday application of freezing point depression is salting roads in the wintertime. Again, the roads are full of ice, which is solid water. By putting salt on it, you are getting an I factor, a molality, a concentration to it, and you can lower the freezing point of it, which allows water to exist as a liquid at lower temperatures, melting the ice. Osmotic pressure is the last of the colligative properties. Once again, the I for the Van 't Hoff factor. Capital M means we're going to use molarity for this one. R is going to be the 0.0821. So again, the R for this is 0.0821 because we're not talking about energy at all. Lastly, temperatures in Kelvin. They do use the pi symbol to represent osmotic pressure. What osmotic pressure is referred to as is the pressure required to stop osmosis. Osmosis is water going from a high concentration to low concentration is a way to think of it for the water molecules. Here's the book definition of a passage of a solvent through a porous membrane from a dilute solution to a more concentrated one. The very last thing to mention for this chapter is it talks about colloids. Colloids are dispersion of particles of one substance through a dispersing medium of another substance. So there's hydrophilic and hydrophobic versions of this. First off, hydrophilic means things that like water. So polar and ionic compounds are hydrophilic. Hydrophobic are non-polar things. Heck, we can go back to biology where you had the phospholipid bilayers, where you had the hydrophilic tails of the plasma membrane. Well, those were polar ends, and then you had the heads of the membrane, which were the hydrophobic ones. Here's a list of several colloids. And aerosols, when you have liquids dispersed within a gas, there's two different versions of a foam. A foam could be a gas dispersed in a liquid, or a gas dispersed in a solid. An emulsion is one liquid in another. A sol is a solid in a liquid. A gel is a liquid in a solid. And then a solid sol is a solid in a solid, which is fairly unusual. Again, I do not know if you'll need to know the definitions of all of those, but again, knowing that a colloid is when you have two substances within each other that aren't completely dissolved is the thing that I'm certain you should be able to aware of. And that is the end of chapter number 12 on colligative properties.